Hi students! So here we go. We're going to do parts 3 and 4 together in the next two videos. What we're going to do is go through the last maybe 19 lecture slides in a bit faster fashion. And what we're going to do after that is go through the worksheets and tools to help us complete the practice question. So again, the first part of the video, the first one you're watching for part 3, is going through these slides fairly quickly because these show us what we need to do. Then, afterwards, using the knowledge we learned from the slides, we're going to practice the practice questions. What you're seeing is the completed version with the answers in them. And of course, what we recommend is work through that question in the blank one. And yes, you can check your answers with the answer sheet, but again, to practice and learn the skills, you gotta start from scratch, or in this case, the blank sheet. So let's remind you again the tools you're going to need. On Canvas, you're going to need your formula sheet. Page 1 is the one you'd want, and we'll mainly be working with independent measures ANOVA. You're also going to need to work with the F distribution. Here is the page for, learning how to use it if you ever forget. And it has a video at the top of the page as well, including the distribution of F ratios. You can also just download and or print the F table itself. This is what we'll be referring to. And finally, for one of our post-hoc tests, the Tukey's honestly significant difference, we'll be using this table as well. And this table helped us determine the value of Q, or the studentized range statistic, for us to complete the Tukey's HSD, or honestly significant different test. Here we go. Let's begin with the slides as part 3 of our video. So we've finished our last learning check, learning the components of sum of squares and degrees of freedom. Sum of squares between and sum of squares within, as well as degrees of freedom between and degrees of freedom within. These are the things we're going to need to calculate our F ratio. So we start from there. Just like we have T statistic for the T test and Z statistic for the Z test, we need F ratios for the F test. In this case, the F test is for ANOVA, analysis of variance. In this case, our distribution of F ratios can be found in that F ratio sheet. And these points are true. If the null hypothesis is true, so maybe like this, okay, so that means, 1 mu 2 equals mu 3, or there is no relationship between the variables, then the value of F will be around 1. Again, F is between group variance and within group variance. I'm just going to write between and within in brief here. Dot, the I. So again, if the treatment effect has the same variance as individual differences, then the F ratio is 1, and would say, yeah, there's no relationship really between the groups. The next point is also true. Because the F ratio is computed from two variances, there'll always be positive numbers. Now, remember how we got variance in the first place. They are sum of squares over degrees of freedom, at least for sample variance. And sum of squares, that means the sum contains the squared deviation scores. So This may remind you of the formula, something like this. I'm going to use sample mean here. And then n minus 1 is degrees of freedom. Because the values are squared, they are always positive. There's no negative values here, and the F ratio is always positive. The last point is also true. When we look at the F table, or the distribution of F ratios, the table itself is organized by two degrees of freedom. The first degree of freedom is the degrees of freedom numerator. That is degrees of freedom between. That's the one with k minus 1. Okay? And then the next one is degrees of freedom within. And that's this. Okay? There's several ways of writing this. The idea is that either you take everybody and subtract that from the number of groups. That means one person from each group. Or you add up n minus 1 for all the groups. Remember, degrees of freedom between and degrees of freedom within, when you add them together, they add up to the total degrees of freedom. For your numerator, degrees of freedom between, that's the columns, so that's up and down. When you look at degrees of freedom within, that's rows, so that's left to right. Keep those in mind, and if you're watching this video and have the sheet handy next to you, you can look for it as you watch the video. That way, you can make sure you get this and know how to practice using the F table or the table of F ratios. Next slide. This is an example of the F table. Here, you can see the F ratio. It's this positively skewed distribution. And remember, all the F values are positive. So there's no negative values here. No negative values. Only positive values. And it just starts from 0, or it starts from 0, and it keeps going to the right. As the F ratio gets bigger or more extreme, you're going to get fewer and fewer, scores in that distribution. Most of the time, you'd get you get scores from about between 1 and 2. And yes, the F ratio can go to very, very large values. If you check your F table, they can be in the tens, the hundreds, and maybe even the thousands. Which is why it's positively skewed. Because there's no negative numbers, and most of the scores are stacked between 1 and 2, and then it's just skews all the way to, very large numbers. That's the distribution that you'll be looking at. So remember, for your F ratio, this is the distribution. It's positively skewed. Whereas for T or Z, you'll be working with a normal distribution with a mean of, either 0 or the mu. Okay? And zeros over on the left for F distributions. Okay? When we do hypothesis testing with ANOVA and look for effect size, in some ways, looking for the effect sizes in ANOVA is easier once you calculated all its components. You only need some squares to calculate them. The same 4 steps for all the hypothesis testing we've done in the past applies here. So take a moment and think back to what those 4 steps are, which leads to the first point. Hypothesis tests in ANOVA also use the same 4 steps as we have used in the earlier tests. So you may remember in step 1, you need to do your null and alternative hypothesis test. Number 2, step 2, we need to set our critical regions. Okay, that's where we need to draw those. With ANOVA, there's also one other thing that's easier when it comes to step 2. There's no one-tail, two-tail test. There's only one-tail test. So we're looking for a positive ratio, and we're going to say, is that ratio far enough on the positive end? Is it extreme enough in the positive direction for us to say, yeah, there is probably some relationship between the variables, or there is some difference between the samples. So you're going to draw something like this and set some critical region with alpha here and your decision here. Okay. You can label those as you remember. Okay. Step 3 would be to compute our test statistic. In this case is the F observed. Step 4 is to compare the observed statistic, F observed, with our F crit and make a decision. Finally, for step 5, which isn't mentioned in the point, but once you've made your decision, you make your interpretation and explain in plain English what that means. Again, if you've rejected the null, if that's what you decided to do based on your F statistic, compared to the critical region, you'd say, yeah, okay, there is sufficient evidence from the sample data for us to say, yeah, there is some relationship between the samples, or there is some difference between them. Or if you fail to reject, then you say, no, there is not enough evidence for us to say there is, a difference or a relationship between those samples. Okay. Remember the components we need to compute the F statistic. We need to do 2 things before we compute the F ratio. Okay. First, we need to compute our sum of squares. So first, sum of squares total, sum of squares between, and sum of squares within. Next, we also need to compute, our variances, or in this case, our mean squares. Mean squares total, we could, but we don't need it. But we definitely need mean squares between and mean squares within. So in the end, we're going to have mean squares between over mean squares within as a calculation for our F ratio. So remember the 2 things we need. We need the steps for hypothesis testing from steps 1 to 4 and 5 for interpretation. And then we're going to need our test statistic, the F ratio. Using the components of sum of squares between and within, you're going to need the sum of squares total to get the sum of squares between. And you're going to need to calculate the mean squares or variance using sum of squares and degrees of freedom. So remember this. That's equal to sum mean square. Once you got your mean squares between and mean squares within, you can calculate your F ratio, which is step 3, your F observed. Again, as a reminder, our F distribution is positively skewed, and we set a critical region depending on the degrees of freedom within and between. So this is between degrees of freedom, and this is within degrees of freedom. Now, on the F distribution, you might notice that, or even the Tukey's HSD test, if you're looking at ahead, degrees of freedom within has another term for it, and it's called degrees of freedom error. Remember, think back to sample error, sampling error. Okay. I'll stick with sample error for now. Bias. So remember this term for degrees of freedom within. for our Tukey's HSD test, that's going to happen later on. But for our F distribution, we need two things. We need to figure out our degrees of freedom depending on our number of groups and also the number of people within each group for degrees of freedom within. Or another way, big N minus K. These are the two degrees of freedom we need for us to find the proper critical value, which I'll call F crit. And the area here, it's all one tail, so you don't have to worry about, oh, do I have to divide alpha by 5? You just have to set alpha, either at 0.05 or in this case on the slide, 0.01. Remember what we learned about alpha. The smaller alpha is, the smaller the probability of a type 1 error. Next, once you've done steps 1, 2, 3, got your F statistic, and 4 made your decision, and you decided, and you have come to the decision based on your statistics that, yeah, there is some relationship between them. I've rejected the no. In that decision, then you can measure effect size. It's the same thing that we've done for Z-test and T-test. So when we measure effect size for ANOVA, we use a related concept, proportion of variance explained. And for ANOVA, instead of using R squared, we use rho squared. Or, sorry, Eta-Squared. I keep saying that all wrong. So, again, for now, whenever you see or hear in the last 2 videos, or 4 actually, said rho squared, yeah, it's Eta-Squared. Regardless, for effect size, we still divide the sum of squares between over the sum of squares total as a way of measuring the proportion of variance explained. It's the same R2 concept, but we have Eta-Squared. So notice here, it's the sum of squares between, which we need to calculate anyway for our F statistic, and our sum of squares total, which we also have as part of obtaining the F statistic. So remember, I'll just write it out for us. It looks like N, but it's Eta squared is equal to sum of squares between. That's the one we're looking for. That's our treatment effect. Anyway, I'm gonna do this again. So our sum of squares between is our treatment effect. And our sum of squares total has to do with all variance, including individual differences and the treatment effect. We're trying to see how much of the variance we see in the entire experiment can be explained or accounted for by the treatment effect.
Makabutang-butang og outgoing message. Kana siya outgoing message sa iyahang kuanday kanang email ba ini ko nga.
Okay, again, we're jumping through the slides to prepare us to complete the worksheet. So, once we've done all 5 steps and measure the effect size, we can actually write it out. So this slide talks about how we would write out our results, the whole test of ANOVA that we've done, including the effect size that follows afterwards once we've decided there is a difference or a relationship. And we include the following things. Okay, so once we decided the treatment means and standard deviations, support, the hypothesis, yeah, there's, we can reject the null hypothesis and saying, there is some kind of difference. We can present it, whether it's in your research methods class. You probably won't be doing ANOVA in your research unless you practice lots and you can do it. And if you can, great. try it. Once you present it though, make sure you include the following things. You need the F ratio, or in this case the F observed, as well as your degrees of freedom. Okay? You also need the p-value, which is calculated, which you can also get. But when you calculate ANOVA, there is software involved that you would probably use, but you can also do it without software. And finally, the proportion of variance explained. So here, this is an F ratio of, okay, some critical value that you can find, and try this at home. See what the critical value is. And this is the observed value, by the way, not the critical one. And so this value is more extreme. The critical value is here somewhere, and the observed value is further than that, which makes it smaller in the distribution. That's why we have the p observed here as less than alpha. This is alpha. Okay. And then we add, since we decided to reject, so we were talking about Eta-Squared, and once you've decided to reject the null, you measure the effect size and include that as well as Eta-Squared. And this would be about 49.2% of the variance is explained by the treatment effect. Okay. So those were the steps. Now what does it look like in distributions? Here's an example. This slide shows you a visual of between treatment variance and within treatment variance. So this is an example here. So as you can see, the left side of the slide, there's one for between treatments, and on the right side you see same experiment, but we control for between treatment variance and we see the overall variance. Okay. For example, if the samples in the first experiment, as you can see here, there is less variability within groups. As you can see, they're all, pretty packed within 2 points away from 3 points away from each other. The range looks like 2 points, and they're pretty close to the mean. And then you can see the mean difference here between them is larger than within treatment variance. So here, just to look, this it's like 4, and this reads like 2. Again, even at a glance, you can see that there is going to be a larger than 1 F ratio. On the other hand, in experiment B, you see the values are much more spread out. The variability for within groups is much larger, and in fact they're probably larger than between treatments. These are probably the mean scores of treatment A and B, or treatment 1 and 2, and you're going to get a ratio that's much more closer than 1. So this is going to give you something like this, much closer than this one. So this experiment is going to have a larger F ratio than experiment B. And that's what it would look like in pictures. So that's it for our ANOVA test. We went through the components, sum of squares and degrees of freedom, between and within treatments, to calculate our F ratio. Once we've made our decision and we decide to reject the null, we can look for Eta-Squared, the proportion of variance explained, using sum of squares between over sum of squares total. So the next step is, okay, if we have decided that there is some effect, we got to figure out which means are different from which one. And we got to figure out a way to do this. So this leads to this slide here. Remember the advantage of ANOVA. We have avoided the cumulative experiment-wise alpha by not doing more than one test, which means we avoid adding up more and more type 1 errors into our experiment by doing fewer and fewer tests, in fact only one. And the way to do that with ANOVA is to pull all the samples together to have one average value for the sample variance, which is why we have stuff like degrees of freedom total, and more specifically sum of squares total, and by extension mean squares total, which is the total variance. So the next step in our logic is that the F ratio measures how much difference there is between treatment means. It's all taken together. Remember, we're doing one comparison for all of them. Okay. And the denominator, the bottom, looks at the variance of scores inside each treatment. Again, we're taking a look at all the samples at once. So what does this mean? Well, the next points in our next slide can tell us more. Again, ANOVA compares all the individual differences simultaneously in one test, again to avoid an cumulative experiment-wise alpha more than what we, want. Next, then when we have decided, there's a significant difference, or in this case, a significant F ratio, and all this says, it says it is at least one difference. At least one. We don't know which one, but there is at least one difference between the groups. Again, we don't know, for example, if it's between 1 and 2, or between 2 and 3, or 1 and 3, if we only compare free samples. Also, that's why we say, and on this point here, we don't know what the F ratio when we deem it to be significant, when it's far extreme enough. We can't actually say based on the F ratio which means, here the key is, which means are different from which other means. Therefore, if we want to find out which means are different from which means, which is probably something you're interested in, it's like, you have 3 pieces of fruit and you close your eyes, you don't see them for some reason, and you judge them by feel. Let's say, for example, with your eyes closed, try to feel the difference between an apple, an orange, and a lemon. Again, obviously in this thought experiment, if you could open your eyes, it's very obvious. Apples are red, oranges are orange, and lemons are lemon, usually. You can have green apples, but I digress. To tell them by feel, you can probably tell the difference too. But imagine if it was, 3 similar types of apples, which you go like, I can know they're different, but I'm not sure which one's which. Or you can compare the weights of the apples. You can go, okay, well, they all weigh different, but I got to figure out which one weighs more. And to do that, you got to be able to make pairwise comparisons again. And this is why we have post-hoc tests. And the one we're going to cover as our post-hoc test is the one that does involve pairwise comparisons. But we account for, an inflated experiment-wise alpha. And that's the Tukey's honestly significant difference test. There's the other test, the Scheffé test, but we're not going to cover that in this course. Okay. So again, a post-hoc test lets us determine which means are different and which are not. So before we go into post-hoc test, there's one more slide here that really drives the point home. Remember, when we do post-hoc tests, they do involve pairwise comparisons. And again, once we make those pairwise comparisons, each time we do it one more, we add the risk of a type 1 error. Alpha increases, which accumulates as experiment-wise alpha right here. So remember, post-hoc test is necessary for us to figure out which means is different from which other mean or other means, but we run into the risk of increasing alpha. Therefore, the post-hoc test that we're going to use, again, we're going to mention two in this video, but we're covering one for this course. The Tukey's honestly significant difference test. And again, these are methods that try to control for experiment-wise alpha. Here is the first one. Tukey's honestly significant difference. Again, rather than doing simple t-tests, which does not control for experiment-wise alpha, by default, if you keep doing those tests, you'll keep adding alpha. And remember what we said, you only need so many tests before you hit 100% alpha. And then that's kind of pointless at that point. So after we've done ANOVA and determined, yeah, we can do or should do post-hoc tests to see which means are different from which, one of the tools that we're going to use for this course is the Tukey's test, or Tukey's honestly significant difference test, HSD. Okay, so here we're using Tukey's test to determine a minimum difference between treatments. So it's like setting a critical region, but the minimum difference here is going to be larger than your critical region, which means we're decreasing the alpha. So even if we did more tests using the Tukey's test, because the minimum difference is more extreme, we are reducing type 1 error, and therefore we're trying to keep our experiment-wise alpha low. Okay? In fact, we're trying to do the Tukey's test in such a way that even if we did all the pairwise comparisons, we try to keep the experiment-wise alpha down, or it won't even reach the theoretical or the one that we expect to have, experiment-wise alpha. And this is how we do it. There's a Q value that we're going to look at, the studentized test statistic, which we're going to use in our Tukey's HSD table. And look at these values again. They should look familiar now. We have mean squares of n, which we can get from our ANOVA test. It's a part of our component. And we know what n is here. It's the sample size. And remember, the n here is a small n, and it's for each sample. Remember, we're doing pairwise comparison, so we need to figure out, what the sample size is within each group. This works best for groups of the same sample size. Once we've determined the honestly significant difference, the large enough difference between the two means, we can use that value as a reference to say, okay, well, if the difference between, let's say, treatment 1 and treatment 2 is smaller than Tukey's HSD, we'd say, no, it's not different. If the difference between the pair of treatments, let's say treatment 2 and treatment 3 is larger than HSD, then there is a difference. So, for example, if we say, mean 1 minus mean 2, and if it is larger than the HSD, then yeah, there is a difference. Or in this case, yes, difference. Okay. So let's say for another comparison, kind of switch the sample here. If the difference between the two other samples are not larger than the honestly significant difference, then we say no difference between those two means. So that's how we would use the Tukey's HSD test, or honestly significant difference, to figure out, using pairwise comparisons that reduces our experiment-wise alpha, to figure out if there are differences between specific means or specific pairs of means. Here is the Scheffé test. It is safer than the Tukey's HSD test because we still try to work around, as you notice here, pairwise comparisons. But we do it in such a way that we use ratios. We use the F ratio again to figure out the significance difference between two treatment groups. So here you might notice is the F ratio of A versus B. So it's like doing ANOVA again, but with two groups instead of all the groups. For our course, we'll cover Tukey's HSD for a few reasons. One, it's simpler to do, but it is not the safest way. And two, if statistics is something you're interested in, there's much more to learn, and we will go through, or in your instructor in your more advanced statistics class will go through this. This course is an introduction to statistics, even though it's called analysis of behavioral data, but it is technically at the introduction level. So let's do some learning checks. I'll read the question first. Which combination of factors is most likely to produce a large F ratio? This is one of those concept questions. Think again to what the F ratio needs. What are its components? Something over something. Take a moment, review the formula if you need to, think about it, see if you can figure out what is needed as a factor or combination of factors to make the F ratio larger. You can pause the video and think about it. Something over something. Okay. Remember this one as well. Okay. Did you figure it out? So again, very similar to what we learned before. Even in t-test and z-test, when it comes to inferential statistics, if there is a larger mean difference between the samples and a small variance within the samples, you're going to get a larger F ratio. Okay. Two more. Again, I'll read the questions to you. Question 4. A. Post-Hoc test. I'm going to change this. Post-Hoc. Post-Hoc tests are needed if the decision from ANOVA is fail to reject the no. Think about that for a second. You can pause the video if you want. Remember, it's fail to reject. Okay. B. A result shows the following ANOVA results. F in brackets 2, 27 equals 5.36. And the P observed is less than 0.05. Read that result for a second, which is something you'd see in, a research article that's done ANOVA. Can you conclude, or you can conclude, that the study has a total of 30 participants? True or false? Again, think about this one, using the degrees of freedom here. Okay, and pause and think about it. So, for A, if you answered false, you're right. We only do post-hoc tests after rejecting the no. Again, we need to determine if there is a difference somewhere, or at least one difference between the samples, for us to make further pairwise comparisons in post-hoc tests. For B, if you answer true, that's correct. remember, degrees of freedom total is all the sample scores minus 1, or you add up the degrees of freedom between with the degrees of freedom within. And then, if you know that, to get sample size, so between was 2 and within was 27. So the total degrees of freedom is 29. So here we got 29, n minus 1, and with the algebra we know n is 30. So it was true. Okay, so again, if you know the components and how they're related to each other, you can read the results very quickly. More importantly, you'll be able to calculate those components, get your F ratio, make your decision, complete your post-hoc test, and, write down or publish your results. There's one last thing I'd like to add here before we finish our lecture slides in part 3. And that's the relationship between ANOVA and t-tests. Here's a scenario as written in the slides. If you're only looking at 2 independent samples, you can do either test really. And they'll still result in the same decision. And there's one more thing that describes the relationship between the F ratio and your t statistic. For any value of, alpha, when we set a critical t value and square it, so for example, if we happen to have a critical value t is 2, when we square that, the F critical value is going to be 4, 2 squared. For you to get this, I really recommend you doing a simple t-test from one of your previous practice sheets. Any pairwise comparison from your independent samples t-test works here. And then for practice, do an ANOVA with it. Do an ANOVA with it and see what critical value you're going to get. And you'll find that it is going to be squared of your critical t value. Again, the critical F value in your ANOVA for that test, when you only compare 2 independent samples, which you have from previous practice questions, the F critical value is going to be squared, not times 2, squared. Now right here, squared. Okay, so t squared is F. Okay, try it and see. This will be one of your conceptual questions to think about, and this also shows the relationship between them. And when it comes to ANOVA, yes, you can do it for pairs of scores or just one pair, but ANOVA is more effective and useful in comparing more than 2 scores or more than 2 samples. Here is a picture form of this. Again, if you got a 2-tailed t-test with an alpha of 0.05, here is, half of alpha because we're doing 2-tailed test. Notice the value here is 2.101. When we try using the same data and do an ANOVA with it and calculate an F ratio, we are going to set the alpha at t squared. Again, there are 2 groups and there's, one factor. So you're going to get the degrees of freedom between and the degrees of freedom within. Try those and see what critical value you're going to get. And it will be squared. Try it and see. Okay. Just going to double check here. And we're done. So, before we review, here are some assumptions that we need for independent measures ANOVA. Measures. Okay. Again, first assumption, number 1. The observations within each sample must be independent. So they're not repeated measures. You're not, doing pairwise comparisons with the samples. None of those. Again, those will be covered in another course. They're independent samples, just like independent samples t-test. Next assumption is that the population from which the samples are selected or gathered are normally distributed. Here, normal means normally distributed. This is common for most statistical assumptions. And it is something that we would assume from the real world. Yeah, we're going to get, a nice spread, a bell curve, if you will, of people from which we choose from. Assumption number 3. This assumption is, for the context of this course, is what we'll assume for now. And we will encounter scenarios even within your textbook, and we will go over those, in another time, where you're not going to have the same variance. And you're going to test for that to see if we can assume this. Okay? But for now, our independent measures ANOVA test assume that the variances between the samples are the same. That way we will not screw up or invalidate our test results by violating this assumption of equal variance or homogeneity of variance. Those are your 3 assumptions. Again, number 1, the samples are independent from each other. 2, the populations from which the samples are drawn are normally distributed. And 3, the variances between the samples are equal. That is, sample groups. The last 2 slides reviews the ANOVA. So again, this is what you should remember seeing before. Your total components, you got your between components, and your within treatment components. You're going to see sum of squares and we're going to derive mean squares for mean squares and mean squares the F ratio. Taken together, which you would calculate, conditions, a number of groups, and you would calculate the total score. You'll get sum of squares total and sum of squares within. From that, you can calculate sum of squares between by subtracting sum of squares total from, or rather, subtracting sum of squares within each score. You add those up and you subtract that from the total to get sum of squares between. Remember how the components work. You put all these together. This is your descriptive, so that's kind of like your step 1 in your practice question. And then you would calculate these values, which by the end of this video, and especially by the end of your practice question, value for each one of these degrees of freedom. You also have a value for between groups, within groups. You're going to have values for between groups and within groups, from which you divide between over within to get your F ratio. Then you can look at it and figure out your P observed. Okay? Good. It's like my son said, good. So that's it. That's the end of our lecture slides. So before we move on to the next video or in our virtual real-time classroom, we're going to go over what we have learned in our Chapter 12 lecture slides. Again, we've explained why we need to do ANOVA and how it works, the logic. We have gone over the components of ANOVA and used it to test the variances for single factor studies. we've described when and why we use post-hoc tests. That is, we do post-hoc tests after we reject the null using ANOVA. We talked about the two types of post-hoc tests that is mentioned in this course and practicing one of them, the Tukey's HSD, SD. And finally, we have learned to calculate the effect size using Eta-Squared. So that's it. That's ANOVA in a nutshell. It is a pretty big nutshell, as in that was quite a lot to cover. And as you can see, that's why we had a whole chapter dedicated to it and a whole lesson dedicated to it. And this can be tested for a whole 3 hours, at least in this course. Remember, if you are familiar with the previous concepts, like sum of squares, even adding up the totals, finding deviation scores and squaring those up to get sum of squares, finding the variance, dividing sum of squares of degrees of freedom, the steps to hypothesis testing, completing those steps, using degrees of freedom to find the right critical values, and other steps listed in your tools, including the bits on independent samples t-test, your transition to learning ANOVA will be that much easier. So after watching this video, you can start practicing the worksheet. And if you find yourself having problems with the worksheet, make sure to go back to the tools list, which is at the very beginning here, to make sure you find your learning outcomes and complete them. So again, make sure you use the tools that you need from your previous previous chapters, especially independent samples t-test, and make sure you use these to achieve your learning outcomes. That's it for our lecture slides in part 3 of our video. This is a long video, about an hour long, probably longer. In the next one, whether we do it in real time or we record one, us doing the practice worksheet, you'll be applying these skills in answering a test or practice question that requires the use of ANOVA as well as the post-hoc test. Again, keep practicing. Make sure you think as you write and write as you think. Make sure you practice by writing and do each step. And if you're using the answer sheet, make sure you use it to check the work that you've done. And don't use it to help you do your work. First, that's cheating. Second, you don't really learn that way. Again, you can do this. Some of you can do this all by yourself and teach yourself this. Excellent. Others may need the help, and so you can email, you can post on the Canvas discussion board, you can leave comments on the YouTube video, contact me directly to get your questions, answered, or you can, better yet, work with your classmates, see somebody that knows the answer there and work together with them. Again, the more you work together, the more it's going to stick. Okay, keep going. You can do this. We're almost done this course, and we'll see you in the next one.